Hello everyone, this is group 3, and we're now going to introduce the slow neutron. First, this is atom. Everything is composed of it, and its core is made of protons and neutrons. Then let's go into the core. Here is the model of neutron, and its thermal energy is 0.025 electron volts. Let's move on to a closer look at slow neutrons. It is the type that a neutron whose energy is lower than a specific value, and the surrounding environment is in a thermal equilibrium. Next, we're going to introduce some field of applications. Slow neutrons refer to low-energy neutrons with thermal energy levels. It's about 0.025 electron volts, whose own energy is not enough to cause ionization and excitation. However, this neutron exists in nuclear reactors. When the material is irradiated in these reactors, it directly causes a number of chemical changes. In reactor physics, neutrons with energy below a few electron volts are usually called slow neutrons. In the application of neutron physics and nuclear technology, neutrons with energy of about 1 kilo electron volts are called slow neutrons. Thermal neutrons are slow neutrons in thermal equilibrium with the surrounding environment. Slow neutrons often appear in the heat reactor of nuclear reactors. Reactors built using the principle of atomic nuclear reaction need to slow down the neutrons released during fission before causing nuclear fission, because the speed of neutrons and the thermal motion of molecules reach equilibrium. These kind of neutrons are called thermal neutrons. The reactor in a reactor that is mainly fission caused by the thermal neutrons is called the thermal neutron reactor, and it referred to as heat reactor. It is a device that uses a moderator to reduce the speed of fast neutrons, make it a thermal neutron or slow neutron, and then use hot neutrons for chain reaction. Because thermal neutrons are more likely to cause fission such as uranium-235, chain fission reactions can be obtained with a small amount of fission material. The moderator is some substances that contain light elements and absorb less neutrons, such as heavy water, beryllium, graphite, water, etc. Thermal neutron reactors generally arrange fuel components in moderators and form reactor cores. And let's talk about neutron cross-section. For a given target and reaction, the cross-section is strongly dependent on the neutron speed. In the extreme case, the cross-section can be at low energies, either zero or much larger than at high energies. Therefore, a cross-section should be defined either at a given energy or should be averaged in an energy range. As an example, the plot shows that the fission cross-section of uranium-235 is low at high neutron energy, becomes higher at low energy. Such physical constraints explain why most operational nuclear reactors use a neutron moderator to reduce the energy of the neutron, and thus increase the probability of fission, which is essential to produce energy and sustain the chain reaction. As you can see in the chart, slow neutron, or you can say thermal neutron, reach the high fission cross-section. A simple estimation of energy dependence of any kind of cross-section is provided by the Ramsauer model, which is based on the idea that the effective size of the neutron is proportional to the breadth of the probability density function of where the neutron is likely to be, which itself is proportional to the neutron's thermal diploid wavelength. Taking lambda as the effective radius of the neutron, we can estimate the area of the circle, sigma, in which neutrons hit the nuclei of effective radius r. While the assumptions of this model are naive, it explains that at least qualitatively, the typical measured energy dependence of the neutron absorption cross-section. For neutrons of wavelengths much larger than typical radius of atomic nuclei r can be neglected. For these low-energy neutrons, such as thermal neutrons, the cross-section sigma of E is inversely proportional to neutron velocity. This explains the advantage of using a neutron moderator in fission nuclear reactors. On the other hand, for very high-energy neutrons, over 1 million electron volts, lambda can be neglected, and the neutron cross-section is approximately constant, determined just by the cross-section of atomic nuclei. However, this simple model does not take into account so-called neutron resonances, which strongly modify the neutron cross-section in the energy range of 1 electron volt to 10 kilo electron volt, nor the threshold energy of some nuclear reactions. Now, let's take a look on the elastic collision equation. It is such a complicated equation. Let's have some transformations. And it's easier now. In 1919, German scientist Otto Hahn discovered that heating uranium-235 with neutrons would split the nucleus into barium and krypton, and three of them. According to Einstein's mass-energy exchange, the tiny mass reduced by this nuclear reaction will be converted into huge energy and released. The chart is said that one of the uranium-235 nuclear fission reaction that produces neutron in a chain reaction. After uranium-235 is hit by neutrons, it absorbs a neutron, which is subsequently split into krypton-92, barium-141, 3 neutrons and energy. When the nucleus is hit by foreign particles, or spontaneously split into several smaller nuclei, it is called nuclear fission, which usually occurs in nuclei with larger atomic numbers, such as uranium-235 or plutonium-239. At last, let's take a look at the whole process of the nuclear reaction. And this is our presentation. Thank you for your cooperation.